See my screen?
Yeah.
Okay. Thank you. Good afternoon to everyone. My name is Thomas Makumbi, and I'm working on the project under RadoNorm. Title is Assessment of Uncertainties Affecting Dosimetric Calculations for the Intake of Radon and NORM. And my supervisors are Bastian Brusted and Christian Stout. I come from ITES, Institute of Thermal Energy Technology and Safety at KIT. So the motivation for this study has been that the adequate assessment of internal exposure to radionuclides is essential for optimization of radiological protection for workers, and also during risk assessment in case of public exposure. And when it comes from the legal point of view or the regulatory point of view, most of these NORM industries have to showcase for compliance with existing regulations. So what happens is that during internal dose assessment and monitoring of workers, the parameters used in the biokinetic and dosimetric models are associated with a lot of uncertainty, basically in the physics involved and the biology, that is the human anatomy and physiology, but also these uncertainties exist in the construction of the models themselves. So now, what is important is that provided the uncertainties can be identified and quantified, one can be able to identify the most influencing parameters affecting the doses calculated by doing a sensitivity analysis. So uncertainty is therefore of great importance if these models are to be considered reliable as far as dose assessment and risk estimation is concerned. But first of all, we need to understand uncertainty. Uncertainty itself refers to the lack of knowledge about a parameter value. So this value is of course fixed, but it is not known with precision. So the uncertainty can be quantified in form of a probability using Bayesian inference or a confidence interval in classical statistics. So the aim of this study, of course, is derived from the title, which is Assessment of Uncertainties Affecting Dosimetric Calculation for the Intake of Radon and NORM. And this objective will be achieved through the following specific objectives. First and foremost, I'll need to do a literature study about the isotopes of radioisotopes or radionuclides of interest. This is mainly radon and its progeny and a few long-lived radionuclides in the uranium and thorium series. Then I also come up with a definition of the typical exposure scenarios for radon and NORM. And after having done that, I'll go ahead and come up with a model for dose calculation that is constructed biokinetic and dosimetric model. Biokinetic and dosimetric models for NORM. And in these models, I'll incorporate the different exposure scenarios and use the models to calculate the dose. And of course, these models will be verified using data from ECR or IR data viewer. Then after that, I'll need to extend this software to be able to account for the uncertainties and sensitivities in the model parameters. So the software should be able to come up with a statistical distribution of the models in terms of shape and size or width. And lastly, I'll use this software to perform uncertainties and sensitivity analysis of the selected scenario. So in my methodology, part of my methodology, like I said in the literature, I'll look at the exposure scenarios. So this picture on the left summarizes the typical exposure scenarios for NORM. The exposure can be classified into mainly three categories. That is occupational exposure for the case of workers working in NORM-involving industries, then exposure to the public, and also medical exposure. Now, during processing of NORM, the workers are exposed to NORM by the fact that they are working with this radioactive material and they are in close proximity to it. Now, the processing itself produces products. So the NORM, the radionuclides are incorporated in these products, which could be like cement, that is material for the building industry, bricks, etc. Now, when this material is used for various applications like building, the occupants in those buildings are exposed to NORM in the form of radon inhalation and the gamma radiation. So now, as the processing of the NORM takes place, there will be public exposure as a result of airborne emissions, that is dark emissions to the public, whereby NORM will be directly inhaled. Also, some of it will be deposited onto crops and forage, thereby entering the food chain. Then there will also be deposition of NORM in water sources, and the waste or the byproduct of these industries, of course, is discharged to the environment, thereby leaching into the soils and contaminating the nearby water sources. So the NORM will also end up in the water in that way, and will be taken up by fish, further entering the food chain. Now also the water will be taken up by the animals, as thereby making NORM to also enter the food chain still. Now the fish will be eaten by the humans, thereby the NORM will be taken up by humans, leading to public exposure still. Now the picture—
You have 4 minutes left.
Okay.
Remember that.
Yeah, a picture on the left, on the right, shows the typical dose assessment process as described by ICRP. Now, if I move to the next slide, we have the concept of the uncertainty and sensitivity analysis. First of all, I will have a distribution of the model parameters. The distribution can be triangular, log normal or normal. And then this sampling of parameters of these model parameters will be applied to the biokinetic and dosimetric models, and we'll be able to calculate the doses. So depending on the value of the parameters chosen, the dose will vary that way, as shown by this vertical variation on the x-axis. So that is basically the concept of uncertainty and sensitivity. So my research plan is as detailed in this table. I'll do a literature review and definition of surveys. So I'll use ICRP or OIR reports and personal research papers I will come across. And of course, the information I'll have gathered in these meetings, and the output will be a report that may take about 6 months. Then the software development, I'll need a computer with the C++ and R Studio, and I'll use ICRP reference models to construct my models as guidance, and I'll also use Monte Carlo simulations. So the output will be the first version of the software that will be able to calculate doses, and the validation will be done on the software. Then I'll extend the software to cater for uncertainty and sensitivity analysis. Still, I'll use similar materials and methods as in the second objective, and the output will be the extended software. Then finally, I'll do the sensitivity analysis for the selected scenarios. Now, these selected scenarios will have to be agreed on by the RadoNorm group. So the output will be a report or a publication, and that may take about 6 months. So far, the progress that has been made, I've generated the first draft of the literature report. And in that report, I've included the radionuclides of interest to me that will be of study, but of course, these are subject to your judgment. Then I've also reviewed literature on the existing models by ECR, as in getting to know how they work and the science behind them. That is the HTRM, HATM, and the wound model. Then I've also reviewed systemic models for Radon and NORM and the typical exposure scenarios and parameter for intake of Radon and NORM. Then I've also done some dose calculation. I've also been able to implement the simplest of models, that is a 3-compartment model. And currently, I'm also learning more of programming in C++ and RStudio. So far that's my progress. I've worked on this project for 3 months now. That's all I had to share with you. Thank you.
Okay, thank you very much, Thomas.